Hello, we're going to look at some normal hypothesis tests today. Now this builds on what we've seen in year 12 of, well, two things I suppose. First of all, we saw binomial hypothesis tests. So that's one thing. We do know what hypothesis tests are. And number two, we've seen what normal distribution is, because we did it early in year 12 and recently revised it. So hopefully we're okay at most of this, but it's certainly different what I'm going to show you. So let's have a look at a starter question. Now this is a starter question which is a binomial distribution. So I'm going to quickly do this just to remind you of what you should already know. Nationally, 60% of 18-year-olds apply for university. Charlotte believes that in her local college this figure is low. Okay, so presumably X is binomial. We'll write that with a B. And then we always need two things. We need an N and a P. The N is the number of people she is going to investigate, and P is the probability of her, or you know, that she is basically the thing she is investigating is right. So to test her belief, she samples 25. So my N is 25, and we've already been told the probability that 60% of 18-year-olds will apply. So we assume that is right, and we write 0.6. I say assume. We basically have a null hypothesis that P equals 0.6, and we have an alternate hypothesis that H1, which is P. Now what she believes that it's lower, so we say that here, and we here write where P is the probability of 18-year-olds going to university. So it's a bit of a pain, but you write out. To see if her belief is correct, then she basically found that 11 went to university. Now I've shown you last year that what we do is we basically draw a line. You don't see this in textbooks very often, but I think this is the best way of showing it. And there was it could have been, of the people she tested, anywhere between 0 and 25 could have gone to university or applied for university. Now we can work out how many we expect to get. That's called mu. It's mu equals NP is the formula that we use, and we'll come back to that later on. It's a very useful formula. And if you do in this case 25 times by the 0.6, well, 25 times 0.6 should be 15, but I might as well do it. 25 times 0.6 is 15. So we expect to get 15. That's what my expectation is. Now, she, when she did her test, only got 11. So you can see it's on the right side of things. She seems right that it is lower. Is it significantly lower? And that's why we have to test this tail. And so we have to find the probability that X is less than or equal to the 11 that she got. That's what we did last year. So I'm going to go here, menu, 7. And we have to press the down. So I'm just going to write these over here. It is menu 7, and we have to press down because we need down because we actually want the binomial CD. So when you press the down, then 1. That's binomial CD. So then press 1. And you always press the variable option, which is number 2. So I shall press that as well. So what is my X value? My X value is 11. You can see that. My N value is 25. My P was 0.6. And basically I type all those in, press equals, and it tells me the probability. So I got a probability of 0.0778. Well, that's about 8%. It says test your hypothesis at the 5% significance level. Well, the first thing to note straight away here is that this is greater than 5%. And whenever it's greater than 5%, that can happen by pure fluke, by chance alone. So we do not reject H0. Basically, Charlotte has not got enough evidence of there being lower rates at her college. I suspect if she got 10, there would have been. So what were my answers? Insufficient evidence, and you need to write this as well. Insufficient evidence at the 5% significance level that the application rate in Charlotte's college is lower than 60%. It probably is, but she hasn't got enough evidence. Normal hypothesis test then. So there are a few differences here. First of all, unlike binomials, we now do not test P, we test for U. Not the probability, but the mean. So we're looking at, on average, what happens. The null hypothesis, therefore, will be written H0 is mu equals something or other. You might be told that on average people are 230 centimeters tall, or something like this. I doubt it. That'd be very tall. And then we've got three different versions of the alternative hypothesis, but basically it's to do with mu again. Mu is not equal to this, or it's less than that, or it's greater than this. Weirdly, we can't do normal distribution with the simple sigma value. So this doesn't work. That's basically we've got a sample mean. Whenever we do these tests, we effectively do a sample, and so whenever we do a sample, our standard deviation is reduced. That's what we saw last time. And when testing one-tailed tests, we could find the p-value. And when doing two-tailed tests, I'll talk more about the p-value perhaps later on, but just be aware that one-tail and two-tail test basically cause us different problems. So I'll do that through example. And the basic premise is we find probabilities. If the probability is less than the significance level, we're going to reject H0. In the same way as we did with the binomial, in our example we just saw it was bigger than the significance level, so we did not reject H0. So that rule will still apply. It's quite a useful fact that that rule will always look like that. So here's my example. It is believed that a healthy level of testosterone in blood is normally distributed. So I'm just going to start off. Have I got a letter for this? It doesn't give me a letter, so I'll go X is normally distributed. Mean of 24 and a standard deviation of 6. So 6 squared for the variance. Always write the variance. Following a race, a sprinter gives two samples. Interesting, two samples. So he does a sample mean X bar 2. You sometimes don't bother writing the 2, but you've got to remember the 2. He does a normal distribution then. It will still have the same mean, but it's because he's got a sample of 2, it's going to be 6 squared over 2 for the variance for his sample. So if we just draw a normal distribution curve, something like that, we're expecting to get 24. What did he get? He got 34. Way, way, way above 24. So on the face of it, he's a drugs cheat. Is this sufficiently high, though, at the 1% level? So a few things here. I should really be writing where X is. And I'll come back to what we should be writing here. So in the same way as last time I wrote where P is, I'm going to come back to that in a bit. But this is definitely a one-tailed test. If it's too high, then we'd brand him, we certainly be very wary of his blood sample levels. So I'm going to say H0 then, mu equals, and we might as well say it equals, we're expecting to get 24. And therefore H1, we'd write mu is greater than 24. And I did say I'd come back to this, probably a good time to do this here, where mu is the population mean testosterone level, whatever it is. Now, we have to test the tail again. It's a one-tail test, so we need to do that probability. So we can do this on a calculator. X bar is greater than 34. Notice I still do the tail. I have to do the tail. So what I'm going to do, I'm going to go to menu 7, 2 for normal CD. The lower value is at 34. My upper value, well, that's infinity, so 99999. And my sigma, this is the bit that people always go wrong on. The sigma will be the square root of 6 squared over 2. So it's the square root. Now you could work that out. 36 divided by 2 is 18. So you could work that out, or you could just type it in 6 squared over 2 as long as you square rooted it. And the mean was 24. So what have I got as a probability? Now it's quite a low probability actually. It's 0.009. and that is less than the 1%. So because it's less than 1, we're going to reject H0. This is sufficient evidence to say that this testosterone level is significantly above the mean. So let's see what my results say. 0.921, is that what I wrote? 0.009. Yes, I don't know why I did that. It's 0.00921. But notice I'm saying that's significantly below what I expected, less than 1%. So we've got sufficient evidence to say that he is cheating, I suppose, or some other things going on. It is known that the lifetime of a certain species of tiger in the wild is normally distributed with mean 13.3. I'm going to do this on the next page. So X is normal, said mean 13.3, and it said the variance of 12.25. Now just remember, that means sigma squared is 12.25. Now if you find that sigma is 3.5, I think. So we are doing a sample to test. It says that we think they will have a shorter expected lifetime than those in the wild. So writing this in the correct order, we'd write H0 mu equals 13.3, and then we'd write where mu is the population mean age of lifespan of tigers. And H1 would say that mu is less than 13.3. This is our belief. We are going to do a sample. It's a sample of 50. Now that makes X bar normal 13.3, and of course it's now 12.25 over the 50 tigers in our sample, and massively reduces our variance. And now we're expecting to get 13.3, but in actual fact we got 12.48. I think it said 12.48. Yes, it did. So we have got tigers which are living only to 12.48. It implies this zoologist is right. Notice I've coloured in the tail again. You've got to find the probability of the tail. The probability that X bar is less than 12.48. That's what we've got to find. So I'm going to go into my calculator mode. So it's mode or menu 7.2, normal CD. My negative 9999 is my lower value, because it's representing negative infinity. I've got 12.48 for my upper. My sigma should be, well, just bear this in mind again, it's this value I use. I have to use this value here. So I'm going to type in, it's the square root of 12.25 divided by 50. Notice I have to use the square root because it wants sigma, it doesn't want sigma squared. And my mu is 13.3. Okay, and what's my probability? My calculator says 0.0488. Now that, what percentage did they tell me to use? They said 2%. Well, that is obviously more than 2%. So we do not reject H0. We do not reject. When its probability is too big, that can happen by chance alone, and therefore we do not have enough evidence. Let's see what it says. Do not reject H0. So exactly the same probability. Good. Insufficient evidence at the 2% significance level that the tigers in the zoo have a shorter lifespan than those in the wild. And notice this bit here, where mu is the population mean lifespan of the tigers. These are the things that we need to write down. Now we've only managed to do really 2 questions on this in the time that we've had for this video. So in class I've got this additional example for us. It's about the lifetime of light bulbs, and when we've done that we'll then look at exercise 18B, and we'll see what questions we can do. We're going to have another look at this exercise as well because there's other things on this. So that's the minimum number of questions I want us to get through. We'll see how we go. All the best.